Hello everyone, my name is Peyman Jabbarzadeh and I want to present a 1.79 approximation algorithm for price collecting a Steiner tree, which is a joint work with Ali Ahmadi, Iman Gholami, Mohammad Taghi Haji, and Mohammad Mahdavi. So let me start with define the problem. So we have a weighted graph and a vertex as a root, and also each vertex has assigned a penalty. And the goal is to connect this the goal is to find a tree such that the weight of the tree plus the penalty of the vertices outside of the tree is minimized. For example, here we selected edges with red color, and the red vertex is outside of it, so we need to pay its penalty. And this problem is NP-hard. There is also a specification of this problem, which is called a Steiner tree, and this one is also NP-hard. So in this problem, we have a set of vertices, we call it terminal, and we need to connect only the terminals. We don't care about other vertices. So it's like that in the price collecting version, we assign the penalty infinity to terminals, and we assign penalty 0 to other vertices. And this problem is also a generalization of the MST problem. So let me talk about the previous work for the Steiner tree problem first. So this problem has an obvious approximation algorithm. We only need to find the metric graph between terminals and then find the minimum spanning tree between these terminals. And this will give us a approximate solution. And there are a lot of works to try to improve the approximation and find better than two approximation algorithm. So let's start with Zelkovsky, which gives 11/6 approximation factor. And currently the best one has 1.39 approximation factor. And actually we use this in our algorithm. We use it as a black box. We can use any STOC24 algorithm, but we want to use the best one. So we use this one here. And at the end, I want to mention that there's no algorithm that can have better than 96/95 approximation factor for this problem unless p is equal to NP. And then for the previous work for price collecting Steiner tree, first I want to mention the Gomez-Williamson algorithm in 1995, which gives two approximation solution and use a pyramidal approach. And this one is crucial for our work, and we use it a lot, and I will explain it more. And also there's algorithm that has better than two approximation, has 1.96. And in this work, we can improve them, and we find 1.79 approximation factor for this problem. Also, I want to mention some similar problems. One of them is Steiner forest. It's generalization of Steiner tree, and Gomez-Williamson again gave a two approximation algorithm for this one. And also there is a price-collecting Steiner forest, which had 2.54 and 3 approximation algorithm by Haji and Jane. And recently there's two approximation algorithm by same authors, which inspired this work, and that's because I mentioned it. And now I want to start with the Gomez-Williamson algorithm, which has a two approximation solution, and I use coloring interpretation to describe it. First, let me mention that we assume that edges of the graph are a curve with a length equal to the weight. And during our algorithm, we maintain a forest such that at the beginning it's empty. We also assign a unique color to each vertex with a coloring capacity of equal to the penalty. And then we define active sets, which are a connected component of our forest that they haven't run off the color. So they have still some color capacity, and you can use them. So basically, our algorithm use this active set, and these active sets color the adjacent edges during our algorithm. And we continue this process until some edge got fully colored. So if an edge got fully colored, we will add it to our forest and merge its two connected components. So we continue this process until there's only one active set which connect root. And if you remember, root has a infinite penalty, so it always is active. At the end, we define live vertices and dead vertices. So basically, dead vertices is vertices that has run out of the color, and otherwise we call it raw live vertices. And we have a prune phase at the end of the algorithm. So basically, we look at the dead vertices. Each time if the dead vertices are coloring exactly one edge of our solution, we remove those solution and all the subtree of that edge. So for example, here, if you look at the red set, and they are only coloring one edge of the forest, so we remove those edges and all of the subtrees. But for example, if look at the blue edge, blue sets, and if they correspond to the dead vertices, we don't remove them because they color more than one edges. So I want to give an intuition why this algorithm give two approximate solution. Let's assume that X is the total time that we use a color of we color with this active sets. Each time that we use this color, so for the optimal solution, if we use a color of some vertices V that is connected to the root, then this vertex is coloring at least one edge of the optimal solution. And if vertex V is not connected to the root, then proportional to the amount of we used its color, which we pay in penalty in the optimal solution. So, and this is for optimal solution. So optimal solution is at least X. For the Gomez-Williamson solution, for example, if we look at some vertex V that is connected to the root in the Gomez-Williamson solution, then on average, anytime that we use color of the V, we are coloring two edges of the Gomez-Williamson solution. And if we don't color V to the root in the Gomez-Williamson solution, then we pay penalty equal to the amount of that we use the color. So basically, we can conclude that the solution of Gomez-Williamson is at most 2x, and it means that it has the two approximate solution. So this was the Gomez-Williamson algorithm, but we modified it a little bit. So we have a parameter beta, which is between 1 and 2, and we divide all penalties by beta. And if we select beta between 1 and 2, then the algorithm remains still two approximation. But the point is that the color of the vertices will run out earlier, which means that we will have more dead vertices and we will connect less vertices to the roots. And why we do this modification? Let's look at the analysis again. So here I write coefficients. So it means that for example, for this one, when we connect a vertex V to the root in the Gomez-Williamson, we are paying two times the color that we are spending for connecting vertex V in the Gomez-Williamson. But in other cases, for example, paying penalty in Gomez-Williamson or connecting or paying penalty for the optimal solution, we are paying one time the coloring that we are consuming. So you see, this one is the problem that makes the algorithm two approximation. So we want to connect less vertices in Gomez-Williamson and pay more penalty. Okay, now let's describe our algorithm. So we have a recursive algorithm that we start with a Gomez-Williamson algorithm, but using the parameter beta, which we don't know now what is the value of the beta. And after we run the Gomez-Williamson algorithm, it gives us one solution. We call it Gomez-Williamson solution. And then we take all the dead vertices and pay the penalty for the rest of our algorithm. And we remove the penalties of these vertices because we already have paid them. Then for the vertices that we didn't have paid the penalty, I mean for the live vertices, we run the best algorithm for Steiner tree problem, which I want to remind that it has 1.39 currently, approximation factor 1.39, and we call it Steiner tree solution, and the tree that we find here. And then if in this phase we haven't removed any penalty, we haven't any dead vertex that we paid the penalty and removed the penalty, so we exit our algorithm. Otherwise, if we had some dead vertices and we have created new instance in this phase, so we recursively call our algorithm on the new instance. So after running this algorithm, we will have multiple solutions and we will return the best one. So I want to explain why we paid the penalty of dead vertices. So if you remember, so dead vertices was the vertices that have run out of their color. They have used all of their color. And the problem is that some of them may be connected to the optimal solution. And this means that we have paid too much cost for connecting these vertices to the roots. So we pay the penalty and we don't care about connecting them anymore. Now we want to see why we need to use the Steiner tree algorithm. If most of the vertices are connected in the optimal solution and also in the Gomez-Williamson algorithm, they were live vertices at the end, so they were connected to the root, and we didn't use all of their color. So in this case, we can try to connect these vertices more optimal than Gomez-Williamson, because Gomez-Williamson has cost 2 times the optimal solution. We use the best STOC24 algorithm and connect all live vertices with 1.39 times the cost of the optimal solution. So, so for the vertices that are in the tree of the optimal solution, we only pay 1.39 cost of the tree of the optimal solution to connect them. But the problem is that because we don't know what vertices are in the tree of the optimal solution, and we are running STOC24 on live vertices, there may be more than there may be some vertices that are live, but they are not in the tree of the optimal solution, and we need to connect them to the other vertices. So we can connect them using the way that Gomez-Williamson are connecting them, and we need to pay 1.39 times the cost of the Gomez-Williamson for connecting those vertices. So that's the intuition for STOC24. So for the recursive call, I want to explain why we need the recursive call. First, let me define R as the recursive instance we create in our algorithm. If you remember, we remove some penalties in each phase and create new instance by setting the penalty of those vertices equal to 0. And if we assume that using induction, we assume that our algorithm is alpha approximation, then we can say that, okay, for the recursive instance, for the instance R, we have alpha approximate solution by calling the R algorithm on it. So the recursive solution we achieve is alpha times cost of the optimal solution for the recursive instance, plus the penalty of the vertices that we paid in this way. And I want to remind you that in the Gomez-Williamson, for vertices that are connected to the optimal solution, when we use the color, we color at least one edge in the optimal solution, and when we use color of the and for the Gomez-Williamson solution, then we use, for example, for vertex V that is connected to the root. When we use the color of the V, we are connecting on average 2 edges of the Gomez-Williamson. Okay. So for the opt it was at least 1, for the Gomez-Williamson it was 2, on average 2. So now we say that okay, for the opt was at least 1. If it is exactly 1, if most of the time active sets are coloring exactly one edge of the optimal solution, then for the recursive instance, for example, if you look at the picture, the red circle is coloring exactly one edge here. So in the recursive instance, if the red vertex is a dead vertex, we can remove the red edge because we don't need to connect red vertex into the root because we have already paid its penalty. So we can show that the cost of the optimal solution for the recursive instance is too much small because we can remove many edges from the optimal solution and have a valid solution for the recursive instance, which is too much smaller than the optimal solution. So in this case, because as we say here, the cost of our recursive solution is alpha times the cost of optimal solution for recursive instance plus some penalty, and cost of the optimal solution for recursive instance is too small, then the recursive solution is good. And otherwise, if most of the time active set are coloring more than one edge of the optimal solution. For example, here you can see the blue set is coloring two edges of the optimal solution. In this case, we can have a better bond for the optimal solution. I mean, previously for the analysis of the Gomez-Williamson, we say that active sets are coloring at least one edge of the opt. But here we say that most of the time they are actually coloring more than one edge of the opt. I mean, similar to the Gomez-Williamson, which color two edges of the opt. So in this case, the Gomez-Williamson actually has a good solution, and the ratio of the solution of the Gomez-Williamson over optimal solution is better than 2. So finally, after we show why we use different solution here, we want to give an overview of our analysis method. So first, we classify vertices based on whether they are connected to the root in the optimal solution or they are not connected to the root. And also in the Gomez-Williamson, whether they are the live vertices or the dead vertices. We also care about, classify based on, for example, if they cut one edge of the optimal solution or two edges of the optimal solution. And after using this classification, we bond all of our solutions in a way like alpha times cost of the optimal solution plus some extra values which can be negative. And then we take a weighted average between the different solutions that we have. And we show that we can find some alpha, beta, and some weights such that if we take the weighted average, this extra value become less than or equal to 0. And this means that the weighted average is at most alpha times cost of the optimal solution. And we do this by putting alpha equal to 1.7994 and beta equal to 1.252. And since the weighted average is at most alpha times opt, cost of the opt, then the best solution or the minimum of them has alpha approximate solution. And, thank you for listening to my presentation.